Normally this is a short section of slides I show at the beginning of class just to give some examples of diffusion, but I didn't get to it the first day, so I thought I'd slot them in here. This is just a really simple cartoon showing diffusion of gas molecules through a polymer membrane. In this case, this is CO2 and hydrogen. Hydrogen's little white molecules, and they're diffusing from a high pressure, high concentration side through the membrane to a low pressure side of the membrane. This is showing a molecular dynamics simulation of hydrogen diffusion through polysulfone, and at even room temperature the polymer chain segments can move in a very restricted fashion, but they do move just due to the thermal energy associated with them, and the hydrogen also has thermal energy, and it's basically diffusing through the gaps created by the segmental motions of the polymer chain. So that's another example of random diffusion. We often think about transport occurring downhill in the sense of from regions of high concentration of a component of interest to regions of low concentration, but there are also cases where you can have so-called uphill transport, where the transport is actually against the concentration gradient. And there's a nice example of that in this paper by Richard Baker. The experiment that's set up is one involving the delivery of a hydrophobic drug, progesterone, across a membrane. Progesterone's hydrophobicity is characterized by its octanol water partition coefficient, or log P value, and that's about 10 to the 3.5 or 3200. And so the progesterone strongly prefers to be in octanol than in water. And this membrane has on one side of it progesterone in a concentration of 10 micrograms per milliliter in water, and on the other side a concentration of 2,000 micrograms per milliliter in polyethylene glycol. Now, if the diffusion were just going to be down the direction from high to low concentration, it would be from right to left, and so the progesterone concentration on the right would go down, and that over here on the left in the water would go up. Exactly the opposite happens. So this is the progesterone concentration in the water as a function of time, and it goes down, down, down until it approaches an equilibrium value shown here. And so the progesterone concentration in the water is dropped by almost an order of magnitude, and it's picked up by a fraction of a percent in the polyethylene glycol. And what this teaches us is that it's not simply the concentration gradient that governs the direction of transport, but it is the thermodynamic activity or the chemical potential gradient. And you can roughly approximate the thermodynamic activity or measure the chemical potential of the progesterone in these solutions as the ratio of its concentration to its solubility limit. And because progesterone is hydrophobic, it has a much lower solubility limit in water than in polyethylene glycol, and so at 10 micrograms per milliliter, the water solution is almost saturated. It has a thermodynamic activity not too far from 1, whereas the polyethylene glycol system is far from saturated. Its thermodynamic activity is only about 2,000 over 20,000, or about 0.1, and so the direction from high thermodynamic activity to low thermodynamic activity is from left to right, and that in fact is the direction that the molecules move. Now, if you replaced the water here, for example, with polyethylene glycol, where the solubility of the progesterone is much, much greater, then in fact you'd see what you might typically expect, that the progesterone would move from the high concentration side to the low concentration side. I'll show you another example of this because it has an important practical application that I'll demonstrate to you. This is the concept of one-way diffusion based on differential solubility. This is a hydrophobic dye, Sudan 4 dye, and it has a octanol water partition coefficient that's approaching 5 million. In other words, if you have this dye and it partitions between octanol and water, which are immiscible. Octanol is hydrophobic and water is hydrophilic. For every 1 molecule in water, there'll be 5 million molecules in the octanol. So really hydrophobic. It's red in color, and in the next slide I'm going to show you a case where I've taken this dye and I've dissolved it into a polydimethyl siloxane. That is a hydrophobic polymer, and then on one side of it I'm going to contact it with vegetable oil, and on the other side water in a diffusion cell. So this is a diffusion cell device. Here's my polydimethyl siloxane membrane with a red Sudan 4 dye in it, and I'm going to put vegetable oil on this side and water on this side, and watch what happens in this time-lapse photo. You see the stir bars in the diffusion cell going here to keep everything well mixed. And if you look at the water, you can't really see any difference at all. And you see that the vegetable oil is gradually getting redder and redder. The Sudan 4 is much more soluble in oil than it is in water, and so it diffuses preferentially into the oil. Not enough of it diffuses into water to even see a perceptible change in the color of the water. Now this movie will run a little bit further, but the situation won't change. The oil phase gets redder and redder. Water, you never see any appreciable dye go into that. Now this is not simply a membrane parlor trick. This has important practical consequences in an application related to coronary artery disease. Here are some of the factors that are key concepts related to a coronary artery disease. Essentially, this is the buildup of plaque in coronary arteries, and then you have a small blood clot that can plug these arteries and lead to a heart attack and injury or death. Historically, this has been treated by simply doing open heart surgery and bypassing these arteries with fresh sections of arteries from elsewhere in the body. This is very invasive surgery. Afterwards, people would put balloons into the arteries and blow them up to press the plaque against the wall, but about 30 to 50% of the time that you do that, you see this phenomenon of restenosis. So stenosis is the narrowing of the artery due to the plaque, and restenosis is that plaque bouncing back out to re-narrow the artery after balloon angioplasty. Later, people started putting bare metal stents onto those balloons, and then when the balloon's inflated, the stent pushes the plaque up against the wall of the artery, and the balloon is removed, but the stent remains in place. Still, 10 to 30% of patients with the stent would experience restenosis. Essentially, when that stent opens up against the artery wall, it injures the artery wall because it stretches the artery, and the body responds with a healing response, much as it would do if you cut your finger, for example, and that healing response attempts to form scar tissue that can grow through the mesh of these stents and reblock the artery. What has changed this and reduced restenosis rates down to near zero is the application of a polymer coating. Here's the structure of one of the polymers that are used onto those stents. It's sprayed on at the time the stent is manufactured, and in that coating is a powerful anti-proliferative drug, or a cancer drug, in this case paclitaxel. And paclitaxel is very effective in cancer treatment because it can arrest the cell growth cycle even at very low concentrations. This material, though, is highly toxic, and you don't want to release it into the systemic circulation. You'd like it to go into the artery wall to suppress the immune response right there locally at the site of injury by the stent. It is very hydrophobic, and the polymer itself is very hydrophobic. The artery wall has a lot of lipids in it, so it looks like a hydrophobic environment. The blood that's passing through the stent is essentially, it's almost all water, in fact, and so that's a very hydrophilic environment. And what happens then is the paclitaxel, dissolved or dispersed in the polymer coating that's on the stent, goes preferentially into the artery wall where it is helpful, and doesn't go into the systemic circulation. This is a movie that shows that, a commercial movie, and so we'll just let it play. So there's the artery with the blockage. Here comes the balloon catheter with the stent on it. It's inflated. Then the balloon's deflated and removed, leaving the stent in place, and the paclitaxel begins to be released from the stent. And you'll see in this animation that it is released only into the artery wall, and that's where it does has its healing power. This movie goes on a little bit longer with some more explanation of this, but this is essentially the picture that emerges. This is one-way diffusion in a very important medical application.